Okay, good morning, dear students. Today we will solve another example of uniform convergence with the help of this theorem. Uh, we knew about this theorem in our previous lecture, and the question is show that the sequence fnx, where fnx equal to this nx e to the power minus nx square x greater than equal to 0 is not uniformly convergent on the interval 0 to k, where k greater than 0. Okay. First we need to find fx. We know about the fx. This is the fx. Okay, for check the for finding the limiting function and uniform pointwise convergence of this sequence of function. If the sequence of function is not pointwise convergent, then it is definitely not uniformly convergent. Okay, so it is equal to limit n tends to infinite, and the function is this fnx, and it is equal to limit n tends to infinite, and fnx is n x e to the power minus, and we can write e to the power minus nx square is nx square. Okay, and when we put n tends to infinite, then this is infinite, and in denominator e to the power infinite is infinite. This is infinite upon infinite, and we can solve this by L'Hopital rule. When we differentiate the numerator, then limit n tends to infinite, differentiation of numerator is x, because differentiation of n is 1, and differentiation of denominator is e to the power n x square, and differentiation of this is with respect to n, then it is x square. Okay, now we can put n tends to infinite. When n tends to infinite in denominator, then e to the power infinite is infinite, and denominator is infinite, and this tends to something upon infinite tends to 0. Okay, this is the limit tends to 0. It's mean the limit exists, and this function is pointwise convergent. Okay, limit exists fx equal to 0 is limiting function, and fx equal to 0 is a limiting function, and this is fnx is pointwise convergent fnx is pointwise convergent to 0. Okay, it means every function of fnx converts to 0, converts to fx equal to 0. Okay, now for finding the uniform convergence of this sequence, mn equal to supremum value of we have the supremum value of this function, supremum value of fnx minus where x belongs to this interval 0 to k, and k is greater than 0. Okay, and minus fx it is equal to fx equal to 0. So the supremum of this is equal to x upon, this is equal to, this value is nx upon e to the power nx square minus 0, then we have this value. Now we need to find the supremum of this function, x belongs to 0 to k. Okay, and for finding the supremum of this function, we are using the same process of the maximum minima. This is y equal to nx upon e to the power nx square. Find dy upon dx. This is dy upon dx. This is dy upon dx. dy upon dx of this function is the differentiation of this function is e to the power nx square to the power 2, and in numerator we have e to the power nx square, and second is as it is nx minus first function as it is and minus differentiation of this is n. Differentiation of this is with respect to this function is n. Okay. Okay, differentiation of this function is, in denominator we have e to the power nx square to the power 2. this is as it is, e to the power n x square, and because we are taking the differential with respect to x, so we can take n common. This n is outside, and differential of x is 1 minus x is as it is, differential of e to the power nx, e to the power nx square, and n and 2x. Okay, now for finding the maximum minima, always dy upon dx equal to 0. Then when we take this is equal to 0, then e to the power n x square minus minus 2 x square and n. This is 2 x square and n, e to the power n x square, e to the power n x square equal to 0, because denominator part equal to 0, and this is denominator because when we take this is equal to 0, then numerator equal to 0. Okay, now this is equal to, this value equal to e to the power n x square is common. We have minus 1 minus 2 1 minus 2 x square and n equal to 0. Now if this is not equal to 0, so this is equal to 0, because the multiplication of two function equal to 0. Then 1 minus 2 x square n equal to 0, and it is equal to 2 x square n equal to 1, and x square equal to 1 upon 2n, and it is, this implies x equal to plus minus 1 upon root 2n. Okay, x equal to plus minus 1 upon root 2n. It's mean this is a point at which, this is a point x equal to plus minus root x equal to plus minus, this is a point x equal to plus minus root 2n is a point at which the function has maximum and minimum value, and then the maximum minimum value of this function is, we can solve this at this point, at this part. Okay, so we have the point is x equal to 1 upon root 2n, this is, and the maximum supremum of this point mn, supremum of this is y equal to nx upon e to the power nx square. When you put x equal to this, then n, because this is modulus function, so we are using the always positive value, 1 upon root 2n upon n, 1 upon root 2n e to the power n, and at the place of x we can put 1 upon root 2n, then it is equal to 1 upon 2n. Okay, 1 upon 2n, and after solving this we have n upon root 2n in numerator, and denominator we have in denominator we have e to the power half, it's mean root e, and the complete solution of this is n upon root 2ne, and because in numerator we have n, then we can write this, we can cancel out denominator root n by numerator n, and in numerator we have n, then root n upon 2e, this is the maximum value, root n upon 2e, the supremum of this function, root n upon 2e is the supremum of this function. It's mean the mn, the mn equal to supremum of this nx upon e to the power nx square equal to root n upon 2e. Okay, when we approach n tends to infinite, then mn tends to infinite. When we approach n tends to infinite, then mn equal to this tends to infinite. It's mean, according our theorem, mn not tends to 0. If mn tends to 0, then the sequence is uniformly convergent, and if mn not tends to 0, then sequence is not uniformly convergence. Okay, in this case mn tends to infinite. When n tends to infinite, the supreme value of mn tends to infinite, it's mean the function is not uniformly convergent. Okay, so the answer of this question is this function is pointwise convergence. This is pointwise convergent but not uniformly convergent. Okay, thank you.